This is a short video on how to use the Phoenix Controller's Thermal Tune application to calibrate an AFM cantilever. From the application menu, select Thermal Tune. As you can see, when the software starts it is already acquiring data. In this case, we can see both the first and second eigen modes of the cantilever deflection. We will want to select the region of the spectra around the first eigen mode of the cantilever. There are several controls on the left side of the panel. The counter at the top shows the number of FFTs averaged to generate this spectrum. Other controls the cantilever type, the medium, air, water, etc., and the absolute temperature. Then the acquisition controls. We usually want to look at the normal deflection signal, but we can select the lateral deflection as well. Other controls the sample rate and the programmable gain setting. Now we need to select the cantilever from the library, or add a new type of cantilever to the library, and select it. Actually, the cantilever installed is an NSC18PT, it is not in this library. We can just add it like this. From the manufacturer's datasheet, enter the name and the length, and width in microns. If the cantilever type was in the library already, we could select it like this. Now that the cantilever type is selected, and it looks like the spectrum is good, we can proceed with fitting the curve, and calculating the calibration for this particular cantilever, using the Sater method. The software does a fit to the spectra data to find the frequency of the resonance, the Q factor, the fit noise and the background noise. The software then calculates the spring constant K, in newtons per meter, then calculates the inverse optical sensitivity, IOS, in meters per volt of the deflection signal. These values are automatically handed to the Phoenix AFM software, when it is started after this procedure. The thermal tune calibrations are used in AM mode, first to select the area of the frequency sweep, and then to calibrate the amplitude of the driven cantilever in nanometers. Thank you for watching.